Let's take a minute and just recall a little bit of elementary matrix algebra here. Let's take a matrix A11, X1. So I've got the first term, the second term, and so on. I'm going to put dots between them here because we don't know how many terms there are in between. But I'm also going to, I'm going to add these up. Okay, so what I'm creating here is a matrix that is actually a an n by 1 matrix. I could go down to a m1, and I've added these all up. So I've got my first row, first column, plus first row, second column terms, all the way up to my first row, nth column terms. And that is a single numerical entry, a single numerical value in a column matrix. It looks longer, it looks like more than that, but if I add, a is just a number, x is just a number, so if I add these all up, then I get a single numerical value. So this is a single entry. This is an m by 1 matrix. It looks like an m by n, right? But I've added these terms together, so it's an m by 1 matrix. It's only one column wide. Now, how might I have arrived at that matrix? I might have arrived at that matrix, that column matrix, by multiplying together, and let's see, an m by something matrix with a something by 1 matrix. So I have an m rows by 1 column. M rows by 1 column. In order for that matrix multiplication to be possible, these two numbers must match. And based on the numbers I have in here, I'm going to want that to be n. So let's go ahead and change that. So if I had an m by n matrix and I multiplied it by an n by 1 matrix, I would get this matrix here. And we've seen this before. Let me add a few more dots here. We've seen this before. This is just backwards matrix multiplication. And so what kind of matrix multiplication might I have to do to get this? Well, the matrices that I would have to multiply together would be these. There is my coefficient matrix. And if I multiply that by this variable matrix, if I do this matrix multiplication, I will get this m by 1 matrix. Now I'd like you to remember that, although this is messy looking, what we were doing in the previous couple of videos was coming up with ways to write m by 1 matrices, right? This is an m by 1 matrix. By doing a transformation on another matrix. So I might be able to say, for example, that this is the transformation of some vector x, tight squeeze there. This is the transformation of some vector x, and I have to know what that transformation was. But when I do that transformation, when I do the arithmetic that's asked of me in order to perform that transformation, I can write that process either this way or this way. I can write it as matrix multiplication. So one thing that I'm going to say about this is that I can either write that the transformation of a vector x can be written as a matrix times a vector x, which is exactly what I have here, right? This is the transformation. This is what it looks like. This is the arithmetic involved. And that's equal to a matrix times a vector. A matrix times a vector. So that's one way we can write that. And another way we can write that is simply to change the way we change the notation we're using for t of x here. What is that transformation? Well, it is itself a vector. So I'm going to call this, I think I'll call it v1. This way it matches what's in your textbook. Sorry, I shouldn't have an arrow on top of that one, because what I'm writing here is the vector v as its components. There's a list of its components. So that's the vector v. I can write this m by 1, because it's by 1, it's a column matrix, right? And therefore it's a vector. I can write this way, or I can write it this way. If I knew what these numbers were, then I would get, when I did all this addition and multiplication, I would get this number here, v1. So I can write this transformation as a list of the rules, a list of the arithmetic I need to do, or I can write it as a list of the results, right? That's how I can write t of x. Or I can write the process as matrix multiplication. So what I'm doing is comparing those two representations of a transformation, right? We can write it as a set of rules, or it turns out we can write it as matrix multiplication. Okay, so what I have here, this transformation, because I can write it this way, we can call this a matrix transformation. And the matrix that we're going to use, addition and multiplication by these numbers, by these variables here, is implied, right? Because if I do this matrix multiplication, then I end up with this arithmetic. So that multiplication and addition of the values in the matrix by the values in this column matrix here, this vector, that arithmetic is implied. But this matrix itself, right, the coefficient matrix, is called the standard matrix. For the transformation. And normally we call that transformation t. As with anything, if I'm talking about functions and I say, oh, we usually call functions f. But as you know, sometimes we need to distinguish one function from another. So we could call them f1, f2, and f3, for example. But we tend to call them f, g, and h. So I might call this transformation t and another one p or q or s, right? I might use an r, I might use a different letter. But if I'm just talking about transformations in general, oftentimes you'll see the letter t. So if I am given a matrix transformation and effectively told what the answer is, or told that the matrix transformation is results in 3x1 minus 4x2, 5x1 plus 3x2, 6x1 plus 0x2, and I'm asked to find the standard matrix, for the transformation t, I may be told that the transformation t is going to be, I can see here that I'm ending up with an R3 vector, right? So that's going on to R3. But I've only been given two variables to work with, x1 and x2, so I'm probably coming from R2. And in many cases, you'll actually be told that the transformation goes from R2 to R3. If I'm asked that kind of a question, asked to find the standard matrix for this transformation, then all I need to do is kind of unpick this. I need to figure out what the numbers are and what the variables are that fit into this matrix and this column vector, this column matrix. Clearly the column vector, let's rewrite it first of all. T of x equals 3, -4, 5, 3, 6, 0 times x1, x2. Now, if I were to take this row and this column, 3 times x1 plus negative 4 times x2, I would get this row here. 5x1 plus 3x2 gives me this column, this row, sorry, and 6x1 times 0x2 gives me this row. So that is this matrix, this 3 by 1, there's only one entry in each row here. There's a sum of numbers. It's one numerical value here. A 3 by 1 matrix written as a 3 by 2 times 2 by 1 matrix multiplication. And the answer to my question then is that this matrix here is the standard matrix for that particular transformation. So that's how you find those. Once you know what the standard matrix is, you can use it to find images of any vector in the space. So now I could do, for example, the transformation of 1, 2 using this t, right? That t right there is this t right here, so it's the same transformation. And instead of writing it out like this, once I have a vector like this, I can just replace this vector here. So that transformation is going to look like this: 3, negative 4, 5, 3, and because I've found this standard matrix, right? I found the matrix I need to do this with. 1, 2 is my new vector. When I do this matrix multiplication, I get 3 times 1 plus negative 4 times 2. That's 3 minus 8, which is negative 5. 5 times 1, which is 5, plus 3 times 2, which is 6. That's 11. And 6 times 1 plus 0. So, having been given a transformation in its most generic form, taken it apart to find the standard matrix that I use to multiply by any 2 by 1 vector. In this case, it's coming from a 2 by 1 vector. I'm multiplying a 3 by 2 matrix onto a 2 by 1 vector. I've identified the generic vector, pulled out the coefficients effectively, and so now I can use those coefficients. I can use that standard matrix on any vector in R2 to find its image in R3. I neglected to point out when I started this particular video that when we work with transformations for which we want to do what we've just done, those transformations have to be linear transformations. So they have to meet the criteria of linear transformations, which are that the transformations have to preserve both the additivity property, where you can either transform the sum or sum the transforms and you'll get the same thing, it has to preserve additivity and the homogeneity property, which means that you can either scale a vector and then transform it, or transform the vector and then scale the result by the same number. So those two properties have to hold before you can talk about matrix transformation. But matrix transformation have their own properties, right? Matrix transformations also have some properties, partly based on the fact that they are linear transformations. We can say that the transformation of some number times the vector is going to be equal to that number times the transformation of the vector. Okay, now here I'm using A primarily because that's what's used in your book. When we talked about defining a linear transformation, we used the number R here, R for real number. I have no idea why they've used an A here when they used an R elsewhere, but that's for consistency with your textbook. I've just chosen to use A. We also have that the transformation of a vector V plus W, again in the earlier section they used U plus V, but I don't know, they're not doing that here. So that is equivalent to taking the transformation of V and the transformation of W separately and then adding them together, you'll get the same thing. And there's a third one listed here, and I don't really feel it's necessary to write this one, but we'll just do it anyway. Looks just like the additivity property for linear transformations, but instead of adding, you subtract. Now, if a vector is negated, pointed in the opposite direction, then added to some other vector, right? Instead of having v plus w, you have v plus the opposite of w, and that's really all that's going on here. There's one other, and your book puts that at the top of the list, so I'll do that as well. If you take a vector and transform it, if that vector is the zero vector, then you're going to get the zero vector out, okay? So if the vector that you plug into the transformation only has zeros for all of its components, then the resulting vector will also only have zeros. I hope that makes sense. I could do a quick example. This transformation is going from R2 into R3. And if I take the first and second component of a vector and do this arithmetic to it, there's two components here. I'll end up with three components here. Add the two components, subtract twice the second component from the first, subtract 3 times the first from the second component. But if the components of the vector are both 0 to start with, then here I'm going to get 0 plus 0, 0 minus 2 times 0, and 0 minus 3 times 0, which is 0, right? So that's just an example. It's not a proof, but I hope that helps you make sense of the idea here. If the input vector is all zeros in a linear transformation, then the output vector is also all zeros. Every component is a 0. And the other three just follow from the fact that this is a linear transformation, right? Homogeneity and additivity are preserved, and this is just a kind of a variation on additivity. So that's where all of these come from, that these matrix transformations are linear transformations to begin with, so these two properties hold. This is a variation of the second property, and this is kind of a new one, but I think hopefully pretty obvious.